Hi, my name is Samuel Benzoni, and I'm a senior at San Francisco State University studying civil engineering.
Hi, my name is Charlie Vidal. I'm also a senior at San Francisco State University studying civil engineering. In this presentation, we will showcase some approaches that we have attempted in order to make our structures smarter for the health of our occupants. The following studies are part of a $1.2 million project funded by the National Institute of Health. The United States is growing older. According to the latest data from the U.S. Census Bureau, over 98 million U.S. residents will be over the age of 65 by 2060. That's nearly 1/4 of the population. Among these older adults, human fall is the main cause of both fatal and non-fatal injuries. From this population, 1 in 4 adults of the age of 65 and older will suffer from a fall, and 1 in 5 of these adults will actually develop an injury due to a fall. Now, this can be very frightening, but in order to seek a solution, we first looked into nature for inspiration. Imagine that you are on a camping site and you hear the buzzing sound of a mosquito around you. At that particular moment, your brain will quickly react and activate different sensory systems. For example, your skin is highly alerted so that you can pinpoint when and where a mosquito lands. When a mosquito does land, you instantly know to hit it without hesitation. With that in mind, we developed a responsive system which can detect a fall in a similar way. This system uses the Wi-Fi signals which exist in every home nowadays, and accelerometer sensors which are common in a structural health monitoring system. The wireless motion component detects motion by analyzing the reflected Wi-Fi signal at each instant. Once suspicious movement is detected, it activates the floor vibration component. The floor vibration component is like the skin in our previous example that is highly alerted. It will then sense and confirm if the activity on the floor is a fall. If so, it will identify the fall location and estimate the fall severity by analyzing the impact magnitude. After that, the floor vibration component will pass that information back to the wireless motion component to monitor if there is any movement after the fall. If there is none, this might mean that the person might have lost consciousness after the fall. This will be an urgent case, and the system will send out alarms to the caregiver and/or the significant others on file. The use of this system provides a responsive solution to the aging population after a falling event. This is great and useful, but can we do better? For example, can we provide a solution to prevent the fall from happening in the first place? We surely can. Studies show that there is a strong correlation between a person's health and his or her walking pattern, or their gait. Being able to determine a person's gait accurately in a home setting will potentially provide invaluable information to infer the resident's health and serve as a preventative measure. The gained knowledge of being able to identify the impact location and its timing from the study of the fall detection system can be tailored and further developed to identify the walking pattern and its gait properties, such as walking speed, step length, or even stride length.
To test our ideas, we developed a test bed in our laboratory. In this setup, we created a grid on our floor for a reference to try and determine impact locations and magnitudes by a person walking. A 30-inch by 260-inch grid was laid out on the floor with nodes spaced out at 10 inches in either direction, creating 27 rows with 4 nodes per row. The black circles shown in the plan view represent these nodes. 6 accelerometers and an impact hammer were used in order to record floor vibration data and were placed throughout the room as shown. The purple circles in the plan view shown above indicate placement of an accelerometer. An accelerometer is a sensor that records accelerations, and we use these instruments to monitor the motion or vibrations of the floor below. An impact hammer is an instrument that will record the force with which you strike an object. We used this instrument to record our inputs or excitations of the floor below. Floor vibration data was recorded for multiple impact hammer strikes at every node. To provide a bit on what's happening behind the scenes, Here's the fundamental equation that the system is based on. The transfer function is a mathematical function that can model the way a structure will react and is defined as the output of a system divided by the input. As our structure can be assumed to be excited within the linear elastic range, its transfer functions will remain consistent throughout experimentation. In creating transfer functions for our grid, we will use the impact hammer data as the input and the accelerometer data as the output. Once we identify the transfer functions between the various grid points and sensor locations, we can then use that information in order to back-calculate the location and force of other impacts, such as footsteps. Thus far, we have performed over 700 experiments to obtain datasets so that we may establish a baseline and start algorithm development. We have also been able to locate hammer impacts with 92% accuracy and estimate the force of the hammer impacts with 89% accuracy. These two plots demonstrate the results of our force estimations. The plot on the left shows force estimations for the area where the impact took place, with all data showing strong cohesion. On the right are force estimations for an area where the impact did not take place. This data does not show very good cohesion and has little agreement. The correlations of our estimates inform our decisions on where impacts took place and lead us to believe the location associated with the plot on the left is where the impact took place. Shown in this slide is how our system reacts to an impact at node 1. First, the identified node is lit up to demonstrate its location. The plot below on the left then shows the force estimations at the correct node in real time. The correlation coefficients calculated by the similarity in shapes of the estimated forces, as shown in the previous slide, are then displayed in the plot shown below on the right. This is to provide insight on possible impact locations. It is clear that node 1 has the highest correlation coefficient and therefore was noted as our location of impact. In the future, we plan to continue to explore various signal processing techniques in order to increase our force estimation and location identification accuracies. Using these heightened accuracies, we'll be able to extract information regarding someone's gait through floor vibrations. In addition to these refinements, we plan on creating a probabilistic model of our floor in order to account for locations where hammer testing may not have been done. After all these adjustments, the end goal would be a live platform product that could monitor activity in an at-home setting. We live in the era of smart technology. We have smartphones that measure our travel distance, smart sinks that monitor our water usage, so why not a smart floor that can monitor our health? Thank you for listening.